So you now have enough to go get started on the homework, and you might want to pause the video here and go get through the first few problems. But I should give you a couple more examples of the later stuff so you can see what that's about. One, there's the graphical interpretation, which can be used to compute integrals sometimes. Let's do this. Let's compute the integral from 0 to 3 of the square root of 9 minus x squared dx. What does that look like? If you think about the graph of y equals square root 9 minus x squared, if you square both sides, you get y squared equals 9 minus x squared. You move that over, you get x squared plus y squared equals 9. Which I don't know if you've talked about this in another class, but this is a circle of radius 3. It's x squared plus y squared equals r squared. Would give you a circle of radius r. Here r is, or the squared version is 9, so the r version is 3. So we're looking at a circle of radius 3. We picked the positive square root, so we actually have the top half of the circle. And we're integrating that from 0 to 3. So we only care about what's happening between the x-axis and 3. Our function, we sort of needed to be able to notice that it was a perfect circle, is why this one's being done by me instead of in the homework. The thing we want is what's the area of this quarter circle? Well, I know the area of a circle. The area of a circle is pi r squared, which in our case is pi times 3 squared is 9 pi. So a quarter circle will be a quarter of that. The answer is 9 pi over 4. Done. Hooray. A weird thing's kind of going on here. That if I actually computed that area, what was our function? It was the square root of 9 minus x squared. Graph me that. Let's go to standard zoom. So I can see, yeah, it's half a circle. It's looking more ovally because the aspect ratio isn't fixed. If I copied it and squared out the aspect ratio, it would be a perfect circle. I can ask my calculator, hey, calculate what's the integral from 0 to 3. And you end up with, it's going to shade in that half circle. We get 0.7068. And if I ask my calculator, hey, calculator, what is 9 times pi divided by 4? It should be the same thing. And it is. Hooray. It actually gave us the right answer. There's a weird thing going on where it feels like we are confirming the formula for the area of a circle that we already knew from high school or maybe middle school. I don't know when you learned that stuff. We're confirming that it gives the right answer. The more reasonable thing to describe what's going on, though, is that we're actually computing that for the first time. When we talked in middle school and high school about finding areas of shapes, it's kind of weird that we didn't actually define what area means in any reasonable way. Like, it's the amount of paint you need? What? Paint's not a mathematical concept. This idea of taking an integral is the first time that finding the area of a circle actually meant something real. Cut it up into tiny pieces, approximate it by those pieces, let the approximations get better and better. This is more the definition of area and finding that the circle does what it's supposed to do for the first time. Or it would be if we actually confirmed that it was 9 pi over 4. So that's a weird thing to think about. The idea of area didn't actually make sense or wasn't on what we would call solid mathematical footing until we had the integral to compute area. That's a weird things are backwards version. The other thing we can do is we can approximate integrals graphically. If I draw a function, let me draw a function that looks like this. And I need some units here. Let's make this 50, 100, 150, 200. And let's make this 4, 8, 12, 16, 20, 24, 28. Let's label this function g of x, and let's say our instructions are to approximate the integral from 8 to 20 of that function. Integral from 8 to 20 of g of x dx. Okay, we could try and read off values and do a Riemann sum. I wouldn't usually recommend that. That's a bunch of multiplying and adding that feels dumb. The thing we understand, is this area, the area under the curve between 8 and 20. We want to know how much area is that. What's this area? Well, a pretty good reasonable way of approximating that area is by counting squares. The thing divides itself into squares pretty naturally. In fact, I can use these little squares. Is that coming out in standard def? I don't know if you can see this on YouTube, but each of those squares is subdivided into 5 littler squares. And the thing I want to do is try to count how many of these squares are inside this region. Well, I have 1, 2... Wait, where's my... I have 1, 2, 3. Actually, let's not count. Let's do some multiplication. I have... This is 6 squares wide by 1, 2, 3, 4, 5, 6, 7, 8 squares tall. So this whole thing is 48 squares in this rectangle. Plus I have another 1, 2, 3, 4, 5 squares here. Plus, and now here's the part where you fall into a trap. You're going to be tempted to try and say something like, well, this is most of a square, and this is a tiny little fragment of a square, and that's 2/3 of a square, and start adding these things up. Most of the time, the answer you get by trying to use your brain's estimate of how much of a square it is pretty bad. A thing that turns out to be way better is treat every partial square as half a square. Some of them will be more than half, some of them will be less than half, but if these squares are small enough, on average, it should average out to be about half a square each. How many partial squares are in our region? We want this is part of a square, so that's 1. We have this tiny little fragment is most of a square. Feels like I should throw it away. Don't throw it away. Just call it half a square. 1, 2, 3, 4, 5, 6, 7 partial squares. Some are more than half, some are less than half, and our brain's judgment at how much of a square is it is usually pretty bad. Letting the law of averages say on average they should be about half a square tends to give you better results. So we have 48 plus 5 is 53 whole squares, and 7 partial squares. So I take 53 plus half of 7, treat those 7 partial squares as if they are half squares. Half of 7 is 3.5. 53 plus 3.5 is 56.5 squares is our answer. Now the second question is, what's a square? Well, to work that out, I go back to the x-axis and the y-axis. What was a square? This distance on the x-axis is 2. This distance on the y-axis is 25. So each of these squares isn't really a square, it's a 2 by 25 rectangle. So the area of a square is 50. So each of those 56.5 squares represents an area of